Hello, everyone. My name is Andrew Garuch, and I am from the University of Waterloo, which is just outside of Toronto in Canada. It's with great pleasure that I'm presenting to you this talk today virtually in the structural components session of the 79th Annual International Magnesium World Conference. The focus of my talk will be the fatigue characterization and modeling of forged magnesium. I'd like to acknowledge the support of the funding agencies and industrial partners who made this work possible. This particular presentation is detailing the nuances of developing a comparison method for fatigue performance of forged magnesium alloys, as well as a reliable life prediction model. But it is also a part of a larger project where we actually designed, analyzed, optimized, and manufactured automotive suspension components from magnesium for vehicle lightweighting initiatives. This presentation will aim to summarize a holistic approach we adopted in this research project known as an integrated computational materials engineering, or ICME approach, that some of you may be familiar with. This is an approach to designing products, the materials that comprise them, and their associated processing methods via linking material models at a variety of length scales. You will see the results from this talk spanning kind of the full range of length scales illustrated in this diagram, but in general, I'll focus on the micromechanics of the research and then gradually zoom out towards the system level to see how the process structure, property, performance relationship interacts with the knowledge development at each of these various length scales. As somewhat of a prelude to my talk, I like to present this photo of the final production component, and it's a production viable component which we produce as part of this work. Not only because this may be visually appealing to some of the audience, it did win a few awards already, but really to emphasize that the main objective of this work, which was vehicle lightweighting. We targeted a fatigue critical automotive suspension component, and we were able to achieve a 37% reduction in mass versus the aluminum baseline. This type of paradigm shifting improvement is not new to any of you in the magnesium field. However, it was only possible due to the experimental methods which we adopted to optimize all the facets of the research process. On the left-hand side of the slide, you can see a schematic of the forging process where intense pressure between rigid dies forces the material to flow in the internal cavities and conform to the desired geometry. This can have many beneficial effects for fatigue, as well as some detrimental ones if the process is not carefully managed, as is done at moderate temperatures between 250 and 450 degrees Celsius. To describe this forging process in more detail, it is composed of the following steps as a part of a progressive multi-step process to manipulate the material geometry and properties. These steps are bending, flattening, die forging, and then machining of the final component. We looked at some of the idealistic preform shapes, such as a flat preform and two types of cylindrical preforms, each of which have their own benefits and drawbacks. We optimized the process in several ways. The forging temperature, as well as the strain rate, were both investigated. Furthermore, we took a mass optimization very seriously, and we took it a step further by intelligently developing the component geometry, which was redesigned specifically for forging of magnesium. We just didn't recycle the geometry of an aluminum component. An overview of my talk can be divided into three sections. The first two deal with the understanding of the effects that kind of the starting material has on the fatigue of forged magnesium alloy. The second is the effect that is most significant in the forging process parameters and that effect on fatigue. Finally, I'll follow up with a detailed method of comparison for using this fatigue data to understand how to design a forging process that will result in desirable fatigue properties or a production-ready component, and the variability associated with forging of real components. Firstly, I'd like to describe the evolution of the properties from kind of the as-received material to the forged material. It is impossible to have kind of one parameter which captures all of these effects that go on into this process, but in general, kind of the microstructural modification due to the processing treatments generally have kind of a mutually exclusive relationship between strength and ductility. In a very general sense, if the strength increases as a result of some processing technique for magnesium, generally it is at the compromise of ductility, as many of you may know. Here you can see kind of the yield strength on the y-axis versus failure elongation on the x-axis, which are two of the most common and convenient yet amazingly significant indicators of fatigue properties for metals, and this includes magnesium. This slide shows the range of tensile yield stress versus failure elongation for as cast um, magnesium materials for three different commercially available alloys from the aluminum zinc family, which are AZ31, AZ80, as well as one rare earth alloy, ZK60. Now is shown is kind of the range of properties for the as extruded materials. You can kind of easily observe here the well documented increase in strength amongst the wrought variety of these alloys. Next shown are the properties for the intermediate scale closed die forgings that were done in this particular study. And that started as a cast variety of material. So this is effectively cast and then forged material. The large variability here comes from the variety of forging conditions that were investigated. Next is the extruded then forged material, which exhibits kind of the superior classification of properties with enhanced strength and ductility. A subset of these data points kind of represent the optimum forging conditions, which lead to kind of the most desirable fatigue properties. The optimum condition in general favors extruded base material with colder forging temperatures, approximately 250 degrees Celsius, and faster strain rates. Next, shown by these red data points is a class of properties for full-scale component forging that was produced using a production-ready method. You can see here a large variability in the properties as well as a slight decrease in the strength due to the kind of the practical constraints that are imposed by forging a real full-scale component. The temperature for forging here was increased to 300 degrees Celsius, which in general improves property homogeneity and ductility throughout the forging, and sometimes can kind of limit the defects that you observe at lower temperatures. Now highlighted here are the properties for AZ31 alloy, which can be seen to have inferior strength and ductility relative to the other two alloys. These are the properties for ZK60 now, which in certain cases exhibit kind of superior yield strength to others, especially when processed via a cast and forge method. Finally, investigating literature for properties of these same alloys, it can be seen that forging has a beneficial effect of both improving the strength and ductility relative to other more common processing methods to produce near net shape components. That is a component that has pretty much the final geometry which will be used in service. This is a significant discovery as a part of our project here, as in general, the strength and ductility are generally thought of being mutually exclusive, as I mentioned earlier. Now that was a lot of information regarding how we went about the project. However, to kind of summarize and better understand the structure-property relationship, I distilled all of the phenomena that I was just talking about into a few key elements. In general, I'll be focusing on a single alloy now for the rest of the presentation. For these comparisons, which will be AZ80 magnesium, as it's found to be kind of the most optimal forging alloy of the ones that were investigated. So now kind of the obvious question you might be asking yourself is what is the difference between kind of the starting point of these forging processes with in terms of cast or extruded material, what should you be starting with? On the left-hand side, you can see monotonic tensile response of as cast and as extruded material on the bottom in various material directions. You can observe that the cast material is kind of identical properties in all three directions. And this differs from the extruded material, which is anisotropic in its response, which is a well-documented phenomenon that many of you may be familiar with. Furthermore, there's an obvious difference between the two, with the extruded material having a much higher strength and enhanced ductility, which is a typical of wrought forms of magnesium alloys. Secondly, kind of these observations are supported by the comparatively higher superficial hardness of the extruded material once forged, which is shown on the bottom here in this contour map of hardness. Due to the kind of the more complex cross-section of this I-beam forging, there will be pronounced spatial variation in the properties, which is a topic I'll discuss in more detail in a few slides. Now extending this comparison towards the fatigue performance of cast and extruded magnesium alloy, as one might expect, there once again is a dramatic difference between the two, which is deeply rooted in these contrasting microstructures, different textures, leading to vastly different cyclic responses. It can be observed here that under strain control fatigue testing in the high cycle regime for a given strain amplitude, the extruded material has a life which is superior to the as cast material by pretty much more than an order of magnitude, which is obviously a very significant improvement. Now, the second phenomenon which I'd like to discuss is the effect of forging temperature on the monotonic behavior, which is kind of by far the most significant processing parameter. You can observe here that in general, higher temperatures, so the kind of plot to the right here, they have enhanced ductility but lower strengths. Furthermore, the increase in material properties is obvious between the as received and the forged materials. So you can definitely see that here in each of the individual curves. So the as received being the black lines and the forged materials being the colored lines. Linking that back to a previous observation, the superficial hardness correlates well with the yield strength of the material in various locations throughout the cross section of the forging. So you can see location A, B, and C here shown in each of these plots. The other important observation is kind of how the base material is modified due to forging. There's a much more pronounced improvement due to forging when the starting material is cast, whereas the improvement when you start with raw material as the base material is somewhat more marginal as one might expect, since the base material in the wrought form already has a lot of the beneficial effects of having a wrought microstructure. Once again, it can be observed that under stress control fatigue testing now, so you can see sigma n here, in the high cycle regime for a given stress amplitude, the extruded material has a life which is superior to the as cast material by more than 10 times once again. Important note here is that the materials being compared are from a full scale forged component, not a specimen taken from kind of an intermediate size forging. The effect of processing temperature is really important in the last step of the thermal history prior to the in-service use, i.e., it isn't the extrusion temperature, but the die forging temperature and subsequent cooling schedule that you use following the forging process that kind of governs the final microstructure that you end up with in the forged component. Although we did look at some post-forging heat treatments in this project, I've chosen not to discuss them here as they're very alloy and application specific. You can simply think of the analogy that the final heat treatment will govern the resulting microstructure, precipitate content, and morphology of those precipitates, as well as the properties. If no specific heat treatment is given in the last step of the thermal history during the forging process, that's kind of what will be replacing it. So as you can imagine, the physical component is a very complex three-dimensional shape, as you can see in the top right here, and thus the local strain and thermal histories are a function of the location within the component, and they can vary quite a bit. Thus, we looked at characterizing many different locations throughout the component to kind of understand the spatial variation and properties in more depth, and how forging a physical component is fairly difficult in terms of material homogeneity and the properties that you end up with. Now overlaying the individual data points over these SN curves or these idealized curves that you can see here, one can easily appreciate that even at the component level of forging, there's a large amount of variability that occurs in the properties, which is highly a function of the location within the forging itself and the thermomechanical history that that specific location experienced. Now to look at all these effects and how they relate to fatigue, here you can see a typical strain life curve that you're familiar with for all three of the alloys in the as extruded condition. So that's AZ31, AZ80, and ZK60. AZ31 in blue has the lowest strength but moderate ductility, manifesting itself here as the lowest life in the low cycle regime at high strain amplitudes. AZ80 shown in red has the highest ductility amongst the three alloys, illustrating the highest life in the high cycle regime at low strain amplitudes. And ZK60 shown in black has superior strength in the as extruded state relative to the other two alloys at the expense of limited ductility. So you can see here how the connection between, or at least roughly the connection between ductility, strength, and the fatigue properties in the low and high cycle regime kind of display or correlate fairly well to what conventional wisdom would dictate. Now looking at the effect of forging to these response curves, you can see AZ31 here has a somewhat marginal improvement in the mid-cycle regime, highlighted by this kind of green region when forged at the optimum processing conditions. The delta between the as extruded and forged curves, as once again, is highlighted in this green area. Now the effect due to forging of AZ80 is more complex, as there is an appreciable increase in both strength and ductility once forged. This dramatic increase in yield strength kind of manifests itself as higher cyclic stresses in the low cycle regime under strain control fatigue testing. This results in a large amount of cyclic damage and strain energy density per cycle, and a lower eventual life. So this is that red region here. However, there exists a transition point around 10,000 reversals where the effect of strength and ductility modification changing as at lower strain amplitudes, the loading is predominantly elastic, and the enhanced ductility causes an increase in fatigue life, as you can see here highlighted by that green region. The effect due to forging on ZK60 is also similar in nature. However, there's a very significant increase in ductility, which causes a dramatic improvement in the high cycle fatigue properties shown by the area denoted in green. So there's a similar transition point. However, we just have this enlarged area in green relative to AZ80, kind of the response shown there. Now, if we extend these observations to kind of a full-scale production component instead of just these intermediate-sized I-beam forgings, AZ80 shows that there is a significant improvement in properties when forging at a slightly higher temperature here at 300 degrees Celsius. This is due to the slightly reduced yield strength combined with the enhanced property homogeneity and ductility throughout the component. So you can see this green area represents pretty much a improvement across the board almost. However, for the production scale ZK60 component, the increase in temperature resulted actually in a decrease in the high cycle fatigue performance. So now you may be asking yourself, is deciding upon a comparison method to optimize the forging technique really as easy as kind of just looking at all these response curves that we were just investigating and the ones that I've previously discussed? Although some very powerful general conclusions can be drawn from that type of analysis, the results that I've shown are really dependent upon the method by which you choose to compare them and the different variables related to fatigue. So kind of keeping that in mind, I'd like to move forward to discuss how to effectively compare the material behaviors and quantify that variability. So you can compare based on a strain-based approach, a stress-based approach, or an energy-based approach, all of which are detailed in a number of different papers that were outcomes or actual productivity from this particular project. So I encourage you to reference those papers if you would like more information. However, what you saw previously was just really a snapshot of a few forms of comparison to kind of evaluate which processing condition would be optimal given the kind of specific performance targets that you have or the property requirements that you have. Given the practical requirements of kind of the engineering application, an optimization function here was developed that incorporates three different non-dimensionalized variables, which incorporate various aspects of the material characterization into one function whose objective is to maximize its value to maintain optimal performance. The first term, phi1 here, addresses the necessity for the component to have high strength and toughness, non-dimensionalizing these individual property attributes against the maximum observed over the wide range of processing conditions that were investigated as a part of this project, allows us to have a term which reaches a maximum of a value of unity or 1. So that's how these terms become non-dimensionalized, as you can see here. The second term incorporates the fatigue behavior of the particular material in terms of the parameters extracted from a typical SN curve that many of you would be familiar with. And then finally, since fatigue is kind of a defect-driven phenomenon, which is governed by the limiting location within the full-scale component that has kind of the most inferior properties. The spatial variation is something that's very important, and we looked at the spatial variation of the hardness or the superficial hardness. That was considered to kind of ensure we have or we select a processing condition that produces uniform properties that are free of major significant defects. So that's the third parameter here, phi 3. Now calculating the magnitude of this objective function for all the investigated processing conditions, the following surface plots were generated to represent the optimization surfaces of each case. So this is cast forged at the top here and extruded forged at the bottom for AZ80 magnesium, which is the most forgeable version of the three alloys that we've investigated. Once again, a value of 1 here on the surface is technically optimal because each of these three parameters or the three terms in this equation are non-dimensionalized. However, you can observe how this result varies as a function of both temperature on this axis as well as strain rate on these axes, which are the two most critical processing parameters as I discussed previously. Selecting the optimum condition here would be that the extruded and forged material processed at 250 degrees Celsius and a strain of 10 per second would be ideal. Important to note here is that the fact that each of these weight factors selected in the objective function are specific for the engineering application that was selected here, and can effectively be tuned or adjusted to meet the requirements of other structural components. So if you're dealing with an aerospace component or a marine component or some other form of component, consumer electronics, obviously these specific parameters can be adjusted to suit the application at hand. Finally, if we impose some constraints upon this optimization surface that you see here, such as the fact that kind of the extremities of very low temperatures and very high strain rates, we observe cracking within the material. So that's one constraint that we can impose here by this gray area. Secondly, at temperatures that exceed 426 degrees Celsius, including the heat of deformation, incipient melting may occur in AZ80. So we can kind of know that that results in inferior material properties, as you might have some microscopic defects within the forge component. So we've excluded this area here. And then finally, the practical constraint of the forging load or the forging press capacity that can prevent forging in very low temperatures, even at comparatively low strain rates. So we might want to impose that constraint there. And this effectively limits our processing window to exclude this gray area, and we will generally constrain the optimum forging condition to be a compromise of all of these constraints, as well as these relative parameters or these thermomechanical processing conditions. You can see how the optimum condition here would shift then. Obviously, this optimum condition will shift here on the surface plot to obtain the next highest value um, once you impose those constraints. Furthermore, although not very significant in AZ80 magnesium, the cost difference between the cast and extruded forms that you might start with prior to forging, so the base material that you're starting with might make another option seem more attractive if cost saving can kind of justify the degradation of performance. So as we previously discussed in detail, going to a cast alloy to start with, you'll end up with inferior properties, but if the cost associated with that might be justified, then that's a decision that needs to get made on the design standpoint. So finally, to summarize some concluding remarks here, of the three commercially alloys or the commercially available alloys that were investigated, AZ80 proves to be superior as a forging alloy. AZ31B has only a modest improvement in properties once forged, whereas forging ZK60 significantly improves the ductility, but not really the strength. However, AZ80 kind of improves across the board and is the best overall compromise of improvement as well as ability of achieving a component while forging. In general, forging at lower temperatures and higher speeds produces material with superior fatigue properties, regardless of the magnesium alloy that's being investigated. Um, Obviously, the specific alloy that you're looking at will have various levels of magnitude in which that statement is true. And finally, the stress, strain, and energy-based fatigue data that we looked at were used as a basis for a comparison for predicting the fatigue performance of forged magnesium components, and this was done with great success. So we encourage you to employ these types of techniques, especially energy-based techniques, which work especially well for forged magnesium components, which is outlined in a number of journal publications that are referenced in this PowerPoint. And with that, I'd like to thank you for your attention and open the floor to the audience for any questions. In closing, I'd like to challenge the audience to kind of tell me a concern that they may have as researchers or as industry professionals towards using magnesium as a material for fatigue critical components. And hopefully we can open the lines of communication and discussion on that topic. My contact info is at the bottom. I'd love to thank you for your attention and have a great day.